So we were doing in noise chapter, or the module which corresponds to noise, which is the module 3. We considered in the last class the different types of noises and some of the problems, and then we considered the noise equivalent bandwidth, the noise figure, noise factor, and noise figure whenever cascaded amplifiers or networks are connected together, and also the numericals associated with them. Part B of the module 3 is noise in analog modulation, where we will consider the noise in each of the amplitude modulation techniques, and then the frequency modulation techniques, and then the phase modulation technique. Okay, all that will correspond to noise in analog modulation. Now, before going to the noise in the analog modulation, we will try to see how we can model a receiver, and then we will consider the noise in DSV-SC, the noise in AM receiver, and the noise in FM receivers. Okay. Generally, whenever we talk about noise, we generally say that when we get back our original signal at the end of the receiver, then in that how much of noise is present compared to what is there, what is the amount of noise which is there in the input side. Therefore, the modeling of the receiver is very much important. So to undertake an analysis of the noise in a continuous wave modulation system, we need a receiver model so as to analyze noise in the continuous wave modulation systems. When we talk about continuous wave, then it means analog modulation only, and that is nothing but amplitude modulation, frequency modulation, and phase modulation. So the customary practice is to model the receiver noise as additive, white, and Gaussian. Whenever we talk about receiver noise, then we generally consider that as the channel noise. Additive, white, and Gaussian. These simplifying assumptions enable us to obtain a basic understanding of the way in which noise affects the performance of a receiver. So whatever we assume over here, the simplified way of assuming a noise as additive, white, and Gaussian will make us to understand what you call the noise effects, understand the whole system, basic understanding the way in which noise affects the receiver, how the noise is affecting the receiver, that we will be able to understand in a better way if we consider the model of the receiver with additive, white, and Gaussian noise. So a receiver model can be considered like this, wherein we have the modulated signal received at the receiver and the noise which is added, WT is added over here, and this noise after getting added, they are passed through the band pass filter to get the value of XT. The XT will have both the signal as well as the noise component. Okay, both these two are filtered, and we get the value of the what you call signal as well as the noise, and then that is demodulated to get the output signal. So ST denotes the incoming modulated signal, right? And WT denotes the front end receiver noise. We generally call it as the noise at the first stage, noise at the first stage of the receiver. That's why we call it as front end receiver noise. The power spectral density of this noise, which we consider as white noise, is denoted by N0 by 2, defined for both positive and negative frequencies, and N0 is the average noise power per unit bandwidth measured at the front end of the receiver. Again, front end just means first stage of the receiver. So the bandwidth of this band pass filter is just wide enough to pass the modulated signal without distortion. So we fix the bandwidth of the band pass filter in such a way that whatever is there here is passed without any distortion. Whatever is there here is passed without distortion. But however, the noise might get curtailed. Okay, WT might become NT. So, but ST will pass through this. So XT will be considered as ST plus NT, where NT is the filtered noise, so to say, and ST is passed directly without any what you call distortion or filtering. So assume that the band pass filter is ideal, having a bandwidth equal to the transmission bandwidth Bt of the modulated signal St. We'll assume that the band pass filter is an ideal band pass filter, having a bandwidth equal to the transmission bandwidth Bt of the, sometimes people will use W, you can use Bt of the modulated signal St and a mid-band frequency equal to the carrier frequency Fc, which is far, far greater than the Bt value. So the idealist characteristic of the band pass filter is written like this. This is the band pass filter with N0 by 2 as the spectral density. SNF is the spectral density, power spectral density, with Bt as the bandwidth. Okay, both positive as well as negative. Center frequency Fc much larger than Bt. The filtered noise NT can be treated as, so this is a filtered noise. Please remember that XT we will try to write as ST plus NT. Okay, that statement we have not written, we might be writing a little later. Okay, whereas here what appears at the input of the band pass filter is ST plus WT, but output of the band pass filter is XT, which is ST plus the NT. And the NT there, filtered noise, may be treated as narrow band noise represented in the canonical form. So WT is wide band noise, NT is narrow band noise after passing through the band pass filter. And that's divided into two parts. One is the in phase component, another is the quadrature component. One is the in phase noise component, another is the quadrature noise component. NIT and NQT, NIT is in-phase noise component and NQT is the quadrature noise component, both measured with respect to the carrier wave AC cos of 2 pi FCT. So we are multiplying with each one of that, the corresponding value. So the in-phase is the term which is used for this because we are multiplying by cos, and quadrature because we are multiplying with the value sine over here, sine 2 pi FCT. So this is in phase with the carrier. This is perpendicular with the carrier over here. That's why we call it as the quadrature component. So the filtered signal XT available for demodulation after filtering, after passing through band pass filter, what we get is XT, and this is available for the demodulator, which is here, right? XT is inputted to the demodulator, and that will be ST plus NT. The average noise power at the demodulator input is equal to the total area under the curve of the power spectral density SNF, right? Power spectral density SNF, and that is 2 into Bt into N0 by 2 is equal to Bt N0. And that straight away, this is Bt into, this is Bt and this is N0 by 2. And definitely this is again Bt over there. So that the whole thing will be 2 Bt into N0 by 2. 2 will cancel. Bt into N0 is what remains. So the input signal to noise ratio, SNRI, is defined as average power of the modulated signal ST divided by average power of the filtered noise NT. This is for the demodulator only. Okay, demodulator only. Output signal to noise ratio, SNR, is defined as average power of the demodulated message signal divided by average power of the noise. So measured at the receiver output. This is measured at the receiver output. This is measured at the what you call input of the demodulator after passing through the band pass filter. We also have the channel signal to noise ratio, SNRC, that is average power of the modulated signal divided by the average power of the noise in the message bandwidth measured at the receiver input. This is measured at the receiver input, and this will be straight away associated with the value of ST and WT. Okay, value of ST and WT. So this ratio can be viewed as a signal to noise ratio that results from the baseband transmission of the message signal MT without modulation, as demonstrated in the following figure. So you have the message signal with the same power as the modulated wave and the noise WT, and you pass it through the low pass filter of bandwidth W, you get the output of this, and this is the SNR C value. So the message power of the low pass filter inputs is adjusted to the same as the average power of the modulated signal. The low pass filter passes the message signal and rejects out of band noise. So we define here a term which is known as figure of merit. For the purpose of comparing different continuous wave modulation systems, we normalize the receiver performance by dividing the output signal to noise ratio by the channel signal to noise ratio, SNR 0 O, divided by SNRC, and SNRC is written over here, average power of the modulated signal divided with the average power of the noise in the message bandwidth. That is the measured at the receiver input, measured at the receiver input. Whereas SNR naught is the value which is considered over here, that is the average power of the demodulated message signal divided by the average power of the noise. So SNR naught divided by SNR C is the figure of merit. Okay, I is not SNR I is not considered in the figure of merit. Now let us see the noise in the DSB-SC, that is double sideband suppressed carrier. So the model for the DSB-SC receiver using a coherent detector is being mentioned over here. You have the DSB-SC modulated signal over here, and you have the white noise, which is known as the wideband additive white Gaussian noise WT considered over here. And you have, we are passing it through a band pass filter to get the value of XT, and XT will contain ST as well as the value of NT. And this is going through the product modulator and then the low pass filter and comes out as YT. To the product modulator, we are giving another term, which is local oscillator frequency for the purpose of demodulation. Okay, and that is cos of 2 pi FCT. So whole of this is a coherent detector or a demodulator. So the amplitude of the locally generated sinusoidal wave is assumed to be unity. We will consider the amplitude of the locally generated sinusoidal wave is considered to be unity. Okay, we will not consider AC, but rather cos of 2 pi FCT, 1 into cos of 2 pi FCT. So for the demodulated scheme to operate satisfactorily, it is necessary that local oscillator is synchronized. So this local oscillator should be synchronized in phase and in frequency with the oscillator generating the carrier wave at the transmitter. So whatever is the oscillator generates the carrier wave at the transmitter, it should be the local oscillator at the receiver should be synchronized with that. We assume that this synchronization has been achieved by some means. Whatever is the means might be, we will have a pilot through which we'll try to generate that local oscillator or whatever method we want to adopt. That's a separate issue altogether. But we assume that synchronization has been achieved. So the DSB-SC component of the modulated signal ST is expressed as, ST is equal to C of AC cos of 2 pi FC MT, where C is the system dependent scaling factor. The purpose of which is to ensure that the signal component ST is measured in the same units as the additive noise component NT. So the additive noise component NT is, the narrow band, so to say, narrow band noise component, which is part of XT. xt is st plus nt. So mt is the sample function of the what you call, this is the message function of the stationary process of zero mean, whose power spectral density SMF is limited to the maximum frequency W. That is, W is the message bandwidth. So SMF is within the message bandwidth W. That is, message is having a bandwidth which is W. The average power P of the message signal is the total area under the power curve of power spectral density. This is a standard formula. P is equal to integral of the power spectral density in the range of the frequencies from minus W to plus W. So we are integrating it with respect to F. So let us consider the example here where we mix, we'll consider mixing of random process with a sinusoidal process. So YF is the output which is generated, and that is equal to xt cos of 2 pi fct plus theta. So this, yt is over here, and correspondingly we'll have the what you call value over here. And if you take the autocorrelation function corresponding to that, you will get Ry tau is equal to 1 by 2 Rx tau cos of 2 pi FCT. So SYF will be the spectral density of the output will be equal to 1 by 4 Sx F minus Fc Sx F plus Fc. So both the frequencies will come out there. Therefore, the average power of the double sideband SC. So these are the two sidebands which are there. Modulated signal component ST is given by C square AC square P by 2. C square AC square P by 2, where P we have seen to be consisting of this, the message power. The average power of the noise in the message bandwidth is WN0 over there. Average power of the noise in the message bandwidth is WN0, or same thing as BTN0. The channel signal to noise ratio of the DSBSC signal is given by SNRC DSB is equal to the value which is C square, this quantity divided by this quantity divided by this quantity, which is written here like this. So next we wish to determine the output signal to noise ratio using the narrowband representation of the filtered noise in T. The total signal at the coherent detector input can be expressed. We already said that xt consists of st as well as nt. St is CAC cos of 2 pi FCT MT, and nt is having both the in phase component and the quadrature component over here. And the output of the product modulator component of the coherent detector is Vt equal to xt cos of 2 pi FCT, and that is nothing but this whole of xt is to be multiplied with the cos over there. And if you do that, then that will generate here a cos squared term, and also you will have a cos squared term over here, whereas this will be sine into cos, right? So this sine into cos will just give you the value of 2 sine, whereas here cos square will be 1 plus cos 2 into 2 pi FCT divided by 2. So if you remove the high frequency component, what you get is only the if you remove the component there, then you will get the corresponding value over here. So xt cos of 2 pi FCT is written over here. We have written that xt into 1 by 2 C ACMT plus half of NIT, and plus of the cos component and also the sine component. So low pass filter, what it will do, it will just remove this component, only it will pass the DC. If it passes the DC, we are going to get only this. Okay, so effectively we have the product modulator and the low pass filter over here. After passing through the product modulator, we will get this over here, right? And if you pass it through a low pass filter, this quantity of FC will be removed and we are left only with this, and that is what is there here. So equation, the last equation, which is the equation 6.8, indicates the following: the message signal MT and the in-phase noise component NIT of the filtered noise NT appear additively at the receiver output. The quadrature component NQT of the noise NT is completely rejected by the coherent detector because we are filtering it through a low pass filter. So we know that note that these two results are independent of the input signal to noise ratio. Thus, coherent detection distinguishes itself from other demodulation techniques in an important property. The output message component is unmutilated and the noise component always appears additively with the message, irrespective of the input signal to noise ratio. So effectively what we are getting is we are just, to this value, the half of NIT is getting added. Noise, the in-phase component is going to get added. The quadrature component is rejected. And whatever in-phase component is added is also additive in nature. It is not multiplicative with respect to the message signal. The receiver output signal YT we have seen is equal to half of CACMT plus half of NIT. So the average power of the message component may be expressed as this. The average power of the noise at the receiver output is measured as 1 by 2 whole squared to WN naught is equal to half of WN naught. So in case of DSBSC modulation, the band pass filter in figure 6.4 has a bandwidth of BT equal to 2W in order to accommodate the upper and lower side bands of the modulated signal ST. Therefore, the average power of the filtered noise NT is considered, 2WN naught. So from the property 5 of the section 5.11, the average power of the low pass NIT is same as that of the band pass filter of the NT. So we'll get back this value over here. So output signal to noise ratio is the ratio of both of them, that is this with this, right? This is the signal and this is the noise, and hence we need to divide one by the other. And if you divide one by the other, you'll get C squared AC squared P by 2W N naught. So we obtain the figure of merit, which is SNR output divided by SNR, so to say, the channel, and that turns out to be equal to 1. And that we have already, derived it for the channel. Okay, channel we have already derived it like this, and we have derived for the what you call output like this. Both are same, and hence we obtain a figure of merit equal to 1. So we will stop at this for